Okay, so the last speaker is Nijso. Could you apologize if I don't pronounce your last name?
Beishuizen.
It's very difficult for me to say. Yes. Thank you for helping that out. He will be talking about wall turbulence modeling. Thank you, Nijso.
Yeah, so thank you, Marco. So yeah, as Marco said, my name is Nijso Beishuizen from Bosch Thermotechnology Deventer, and I'm also a part-time assistant professor at TU Eindhoven in the Netherlands. And yeah, my talk is about turbulence modeling near the wall, and specifically about the implementation of wall functions in SU2. So I will briefly go through the theory of where of boundary layers and where wall functions come from, and then I will show some validation test cases. So let's consider first the turbulent flow over a flat plate, starting with a uniform velocity profile. And the velocity profile over the plate is only non-uniform in a thin region close to the plate, which is the boundary layer. And at the start of the plate, the boundary layer is laminar, but further downstream, the flow transitions into a turbulent boundary layer, depending on the local axial Reynolds number. Now, in the turbulent region, the self-similar velocity profile can be divided into a viscosity-dominated sublayer closest to the wall, and an inertia sublayer where viscosity is basically negligible, and the outer layer where the flow is not self-similar anymore and governed by, let's say, global flow features. So very close to the wall, a thin boundary layer is present, which is characterized by very steep gradients, and this means that in simulations, many cells are needed very close to the wall to accurately compute the gradients and the velocity profile. So what does a typical velocity profile at the wall look like? So let's assume we have obtained detailed velocity profiles at the wall from measurements or simulations, and we can normalize the distance from the wall y and the velocity u using the local shear stress tau w at the wall and the viscosity at the wall. And if we then plot this, then these velocity profiles turn out to be universal for any wall-bounded flow where we still have a nice turbulent boundary layer, of course. Now, in the viscous sublayer, the velocity, the normalized velocity is linear in the normalized distance y plus, and this behavior transitions after some buffer layer into a region where the velocity follows a log law, which was already investigated by Spalding in 1961. Now, the maximum y plus, where the log law does not hold anymore, depends on the Reynolds number, and all regions together can be described by a simple universal formula determined by Spalding. So how can we use this universal law of the wall information in CFD simulations? So it's actually a very simple algorithm. We have the universal law of the wall with coefficients kappa and b coming from measurements or very detailed simulations. And in our CFD simulations, we retrieve for the first point away from the wall P1, the distance y1, and we normalize this into y plus. Then we iteratively get u plus belonging to this y plus, and then we compute the wall shear stress. And this gives us then a very accurate depiction of the shear stresses. So some simulation results for this figure shows the numerical results of running the SST 2003 turbulence model for the incompressible flat plate using different mesh sizes, where the mesh was varied in such a way that the y plus value for the first point away from the wall changes from 0.1 to 1 and then finally 10. And each point represents an actual point in the mesh, taken at a vertical line a certain distance downstream of the start of the plate in the region where we are actually in the turbulent boundary layer regime. And we see that the mesh with y plus is 0.1 and y plus is 1. So the finest meshes follow the Spalding formula very well. And we see that all the way up to y plus is 1,000 we follow this universal law of the wall. Now for y plus is 10, however, the velocity profile is clearly wrong. And so you can also see in the figure that the first point starts here at y plus is 1, and then we have a large deviation from the velocity profile. Now, if we use wall functions for using y plus is 30 or even y plus is 130, the velocity profile matches again with the result simulations very nicely, even for y plus larger than 1000, where Spalding's formula does not even hold anymore. The skin friction as a function of Reynolds number is shown here, with in dashed red the theoretical turbulent skin friction from white, and in blue the laminar skin friction, the theoretical formula from Blasius. And to capture the laminar low Reynolds region at the start of the plate, we would need a transition model, which will be talked about tomorrow. But we did not use a transition model here, so the focus is on the performance for high Reynolds numbers. So we first look at the results without wall functions, where we have to rely on resolving the velocity profiles with a very fine mesh. And we see again that for y plus is 0.1 and y plus is 1, the theoretical skin friction is approximated very well. And we also see that for y plus is 10, the skin friction is heavily under predicted. Here it's all the way down there, this green line. But with wall functions, we basically get the same result as for the wall result simulations almost as soon as we are in the region where the turbulent boundary layer starts. So let's say from let's say Reynolds 500,000, we already get very good results. And now wall functions were also implemented for the Spalart-Almaraz model. In this comparison, we see in blue the SA model, and in orange the SST model from the previous slide. And the solid lines are the wall resolved simulations with y plus is 0.1. And then the lines with the markers are using the wall functions with a y plus of 30. And we see that also SA performs as well as SST. Compressible flows. So the wall functions were also implemented for compressible flow, where in compressible flows also frictional wall heating is taken into account. Now for this very low Mach incompressible flat plates, wall friction is negligible. So we will not see any of those effects here. But we do see that for the compressible model, also we see a similar good performance. We see that the prediction of skin friction is slightly lower compared to the incompressible results, but the predictions improve when the y plus reduces a bit. So for y plus is 6, we retrieve almost the same results as the fully resolved simulations with y plus is 1. Of course, we have much less nodes in the total mesh. We also see that without wall functions, the skin friction is completely wrong if we use a y plus is 10. So very important to use the correct amount of cells near the wall. Now, heat transfer in many applications very important. So the thermal boundary layer is actually similar to, but a bit different from the momentum boundary layer. So we actually expect a kind of law of the wall for the normalized temperature. So what does that look like? Here we see again the normalized velocity, but now for a heated plate, where the plate was heated from 310 to 600 to 900 Kelvin. These results are for the wall resolved incompressible SST model. And as the temperature of the plate increases, the velocity profile becomes steeper, moving away from the universal Spalding formula already quite early. So this universal formula actually does not hold anymore for a y plus of let's say 10 to 20. Now the wall function model actually gives a good prediction compared to the wall resolved SST model, but for very high y plus values, so far away from the wall, we overpredict the velocity, and the reason is that we previously did not take into account a wall model for temperature, but only for velocity. Now, if we also correct for temperature, then we see that the velocity prediction with the wall functions is again matching with the wall resolved SST model. Now here we see a figure of the normalized temperature, and it shows how the temperature behaves between the flat plate temperature and the free stream temperature. We can then again normalize it in such a way that T plus looks similar to a U plus, and we see that when the wall temperature is increased, T plus profiles steepen further away from the wall. And for small Y plus values, the temperature profile is linear like the velocity profile, but now with also a dependency on the Prandtl number. Now different correlations for the temperature profile exist that are similar to Spalding's formula, and here I only show a much used correlation from Cater, which also has a Prandtl dependency. Now the skin friction, where we include wall heating, shows a similar behavior. So the skin friction reduces according to the square root of the ratio of the wall temperature over the free stream temperature, which is a known theoretical result. With only wall functions for momentum, we underpredict the skin friction, but using wall functions for temperature gives, again, a very good match. Now, to show that we can also use this for a little bit more complicated flows, here I will show some results for a 90-degree bend from the literature. This is a very interesting case because in this bend, we also see, so the flow is coming from the top and flow going around the bend. Then in the bend, we have some flow separation. Later on, when we almost are out of the bend again, into the straight section, we get flow reattachment again, and we have two counter-rotating vortices, which are called Dean vortices. Now, in this bend, velocity measurements were obtained experimentally in several planes before, in, and after the bend. And we will look at a couple of these planes that are shown in this image. So these are the results for the wall-resolved SST model. Y plus is 1 here. It shows a very good match with the experimental data, considering that it's quite complicated. We captured the main flow features, but we also see that our central core here, it compresses a little bit faster and moves a little bit more towards the inner wall compared to the measurements. Some results where we increase the Y plus value, so the first, so the distance from the wall to the first point away from the wall. So we see that for Y plus is 5 and Y plus is 10, we actually still have reasonable results, but for Y plus is 30, the results are very bad. Now, when using the wall model at where we use Y plus is 30, we again get a much better performance. So if we compare it with the experimental data as well as with the wall resolved simulation results, we see that the wall model compares quite well in this comparison. 2 minutes. Okay, almost finished. So you can also do some more quantitative analysis. We again see that it matches well with literature results. What do you need to do to unleash the power of wall functions? It's very simple. The only thing that you need is to add this keyword, marker wall function, then the name of the wall that you also use to define, the isothermal wall or the heat flux wall, and you just say it's a standard wall function. And if you feel like an expert, then there are also some expert parameters for you to play with. And this is all already in develop and ready for use. So to conclude, wall functions were implemented for compressible and incompressible, for SST and SA. For the compressible solver, we also take into account frictional heating. Of course, feel free to do some validation for supersonic cases. So what is still to be done? I did show already some results for heat transfer, but that still has to be merged in the development version. And also, it's known from literature that these wall functions can also be improved when we have, let's say, more complicated situations like stagnation flow, flow separation, and reattachments. Now, thank you for your attention, and I hope you will all try out this new wall function model. Thanks.
Thank you very much. Very good. Thank you, Nijso. We have a few minutes for questions. Alberto, please.
Thank you and for the work. We are very involved functions, especially for simulation. So the transfer for us is very important. We use them when we validate against for results, including E-class from leaders for the detection system. That's really what we are very interested. Thank you very much for this. It's something about roughness in the model.
Yes, so
Maybe just let me repeat the question for the people online. So the question is looking at how roughness could be incorporated into this wall modeling function. Is this correct?
Yes.
Yeah. Okay. So for the wall resolved SST model, there is wall roughness implemented, but this has not been implemented yet in the wall function model. But this has of course been studied a lot in the literature, so it is known how to do it, let's say. But somebody has to do it. So, thank you for your volunteering. Yeah.
Yeah.
Okay, very good. Very good. Yeah. Now, some work needs to be done.
Work is significant. Maybe.
Yeah, sounds like fun. Yeah.
Thank you, Alberto. Another question? Yes, there.
It goes on my side. I'm very useful in the relation to many. My question is regarding the using this feature for example, for instance, what kind of well-line treatment in case you would have this shock interaction.
Okay.
Who you are representing for?
Okay, so the question is now looking after the applicability of this approach of wall function in the case of supersonic flow and, for example, in the case of shock wave boundary layer interaction.
Yeah.
Is it correct?
Okay, thanks, Matteo. That's actually a very good question. So the original paper of Nichols and Nelson that this implementation was based upon, they actually have a couple of validation test cases in their paper for compressible flows. But I didn't feel comfortable enough in the compressible flow regime to actually do those validation test cases. So there are two answers. One is we should not assume that it works until it is validated. But two is, according to the paper, it should actually work up to a certain let's say level. For instance, we also saw in the previous talk that density effects in compressible flows could be also important. So we might also need to use a specific SST models where we also take these effects into account first.
Okay, thank you. Yes, last question, please.
Thank you. I was wondering what's the effect are on the fish costs when you look what you get for these fuel cells or the effect that you went through solving the equation. So what is it?
Yep. Very good question.
Okay, just repeating the question here. So the question is now looking after the computational cost of the use of this wall function approach, because there is the benefit of reducing the number of points, especially when you get close to the wall, but you have an iterative process that you have to work through.
Yeah, so actually the iterative process is very cheap. So the computational cost, so there are two benefits. One is we have much smaller mesh sizes. So in the flat plate, the mesh size can be reduced by a factor of 4, and we get the same results. The other thing is the if you use wall function, it converges much faster if you look at the total number of iterations. So I'm not saying that this is a general thing, but that's something that I observed for the cases that I ran, that it converges about 3 times faster if you look at the total number of iterations, and it looks like the yeah, exactly. So the stretching is because of the cell stretching. Yeah, yeah. So yeah, the computational cost is about 10 times lower in the cases that I looked at.
Very well. Thank you, Nijso. Anyone? Very last. Okay.
More comment than well, I'll throw one question on. I think a couple of people picked up on this. This is one of the features that we've been trying to implement in the software since, I don't know, 2015. I don't know when we started, but I just want to say thanks to Nijso for picking it up and finishing it. And these kinds of initiatives are great when we can share it amongst other people. So kudos on that. And then my question was, you showed SST kind of going off at Y plus 30. Do you know when SA goes off? What Y plus?
Yeah, I think more or less the same location. Maybe I even have some figures if you're interested. Maybe I didn't. Maybe they're even included here. I can check. No.
SST is supposed
No.
to be a little more forgiving.
Yeah, so this is actually the skin friction for SA. So here you see that if we use SA with a Y plus is 10, then we see the same as what we saw for SST, that the skin friction is like super low. So it looks like it's more or less the same performance.
Thanks.
Very well. Thank you very much, Nijso. Once again.